Welcome back to more smart contract vulnerabilities here. We're taking a look, more into the delegate call vulnerability. In the previous video in this series, we looked at just some of the fundamentals that you need to understand to know what's happening here with this vulnerability. It's pretty complex, as you can see here. Just a quick refresher, we have a Fibonacci contract here, which is going to be used as a library for this contract right here, this Fibonacci balance solidity contract. So in here, we got a number of things happening. Basically, we, without stepping through all of this and getting too far in the weeds here, we are just going to withdraw Ether from the contract based off of the Fibonacci numbers. So this contract here is actually importing the Fibonacci lib contract here, and it's just doing based off the Fibonacci numbers. It's actually returning and withdrawing from the actual contract based off of those mathematics there. And now basically what we have here, right, we have the signature variable, which is the kekak or SHA-3 hash of the string. And that's the function selector. They put that in the call data, specify which function will be called. So in this case, we are using the delegate call, right? And this is where the vulnerability comes into play, just because of how delegate call works. That was something we were also looking at in the previous video. So that might be a good refresher if you need it. The previous video in this series. So basically the main issue with all of this, right, is the start and the set start, right? So you notice that the state variable start is used in both the library and the main calling contract, right? So in the library here, we use the start variable here, and there's the set start function. And then we also use we also use the start variable here. Now, in this contract, we're actually hard coding start to be equal to 3. But actually here, it's a different assumption is made. Right. Yeah, so here we are initializing that variable based off of the set start function here. And if n equals 0, we return start. Otherwise, we increment the variable. So that's basically the difference here. We're initializing this variable and assigning it to this setter, basically. Whereas here, we're hard coding that value. Now, the main issue is, right, the way that delegate calls actually function. So the start is used in both the main and library, right? In the library, it's used to specify sequence set to 0. And then in the Fibonacci balance, as we saw, was 3. So because of that, the fallback function allows all calls to be passed to the library contract, allows for set start to also be called. So the issue with this is that there's a discrepancy in the value of start. And so basically what they're explaining here, right, we preserve the state of the contract. It may seem that this function will allow you to change the state of the start variable in the local Fibonacci balance contract. If so, this would allow one to withdraw more Ether as the resulting calculated fib number is dependent on the start variable. Remember, as we saw that in the library contract with the setter there. So the actual fact of the matter is that the set start function does not and cannot modify the start variable in the Fibonacci balance contract, right? And basically they're explaining how this is actually can actually be a lot worse than just modifying the start variable, right? And they go into the actual issue. And here's where things get if that was a little bit difficult to follow, here's where things get yet even more complicated here. Now, this part here, this paragraph was just going over the way that state variables are used in storage, the layout in storage, right? And we've covered that in the previous video, so I'll kind of gloss over that. And so yeah, looking at that library contract, there's two variables, start and calculated fib number, okay? First variable is start. As such, it gets stored in the contract storage at slot 0. Remember, it's 0 indexed, these state variables, right? And second variable gets placed in 1, right? So 0 index incrementing by 1. And so if we look at the function set start, it takes an input and sets start, right? It's just like a basic setter, basically, to whatever the input was. This function is therefore setting slot 0 to whatever we provide in the set start function. So similarly, the set Fibonacci function sets calculated fib number to the result of Fibonacci n. So again, it's just simply setting the storage slot 1 to the value of Fibonacci n, so on and so forth, right? So as you see here, these storage variables are not corresponding to what you would typically expect. Slot 0 is actually going to correspond to Fibonacci library, while slot 1 will correspond to the calculated fib number, okay? Because we're dealing with a delegate call, it preserves contract context, okay? So any of that code executed via delegate call will act on the state of the calling contract, right? And so that's where you see here the example, line 21, right? Calling the set Fibonacci function. And that's going to modify storage slot 1, which is, in this context, the calculated fib number. And the start variable is actually going to correspond to Fibonacci lib located in storage slot 0, right? So we can actually get an unexpected result from Fibonacci, the Fibonacci function here, right? Because of just how it's referencing start slot 0, right? Rather than what you would actually expect if you didn't run this with a delegate call, if you did like with a library instead. So we can get the withdrawal function to revert because it's not going to contain the amount of ether, right? uint Fibonacci library, which is what calculated fib number will return. Okay, and it does go a little bit beyond that, let's just say. So here they explain that you can actually use this fallback function to basically run anything you want, as we'll see here in a second, right? Because basically what the fallback function is if you try to run a function and that function doesn't exist, it will instead run some code. So there's a pretty serious vulnerability here, as you might be able to guess here. So attacker create a malicious contract, convert the address to a uint, you can do that in Python, right? And then call set start, passing in attack contract address as uint, and then change the address of the attack contract. So whenever you call withdrawal or the fallback function, it will run the malicious contract instead. And so, for example, as we will see here in the POC, you can use that contract to create a contract to steal the entire balance of the other contract, right? So that's basically what we do here. We have our own contract here, our malicious one, that's going to steal all the ether out on the fallback function, right? The fallback function, as they explain and as I mentioned, is the function that will run if a specified function is not found. So in this case, we're going to use this to steal all of the ether, send it to our attacker address, right? So and that is basically what is going on there. So this will modify calculated fib number by changing storage slot 1. So there you go. Basically, the preventative technique here, remember, delegate call, state preserving, right? So these aren't variable names. Yeah, this is an important distinction here. These are not actually variable names of the contract. Rather, they're the storage slots which those names point, right? So remember, we can actually preserve variables between contracts, right? That's what state variables are. So quick refresher there. Now, the preventative techniques, just don't use delegate call in this situation. Could have some unintended consequences, as we saw. Instead, you're going to want to use the library keyword to implement these kind of library contracts, right? And that's a safer way to do it. That way, it will not behave in that way, in that manner, right? And so an example here was the parody multi-sig wallet hack. And so the thing is, right, the code was well written. The library, that is, the library was well written code, but the contract that was using that library was using a delegate call. And as we see here, can have some issues when you do that, right? See right here, the delegate call for this wallet contract. And this is the line here that makes this oh so vulnerable, right? And so basically, the hack here is pretty similar to before, only that it was a real-world example of where you could actually withdraw Ether from the wallet. Obviously, a pretty bad vulnerability if you have a wallet and you can't keep the money on there. So yeah, hopefully this video was of help to you guys. I know probably getting kind of lengthy here, and there's a lot to digest with this vulnerability. This is one of the more complex ones, to be quite honest. So if you made it through this video, give yourself a pat on the back. Maybe even dig into this on your own if you really feel that you need to. And yeah, when I see you guys in the next one in this series, we'll be covering default visibilities. So pretty interesting one. See you guys right over in the videos on screen now if you want to catch up on some of these in the series. Maybe you haven't watched to this point. You just clicked on this videos in your browser or whatever. I'll see you guys over in those videos. Thanks for watching.